We are happy to have Mateo Galdeano from Oxford University, who is going to tell us about families of solutions of the heterotic system. Right?
Yeah, that's correct. Thank you very much, Carlos. So, first of all, thanks to the organizers for inviting me. I'm very, very happy to be here. You know, as a PhD student during pandemic, it's my first in-person talk. And so it's very, very exciting. I'm very happy to be back at ICMAT. So as Carlos was saying, I'm going to talk about families of solutions of the heterotic issue system. Yeah, first of all, I should say that it's joint work with Xenia de la Osa, with my supervisor. Yeah, so, well, first of all, about the structure of the talk. So this is going to be like a cooking show. We are going to, so I'm going to be the chef today. I'm going to tell you what do we want to cook up. And I'm going to give you a recipe to do it. And then I'm going to show you how I do it. I'm going to chop some vegetables, throw in some things. And then it will be some magic process where it goes into an oven. And then I'll show you the result. And you have to believe that I've actually prepared them anyway.
We'll have for coffee, right?
Yeah. And then we'll go for coffee. Exactly. Hoping that I finish on time. I'll try to do. So, so what's on the menu today? What we're going to try to construct is some supergravity solutions with minimal supersymmetry. So some background solutions of heterotic supergravity with alpha prime corrections. In particular, on this background, something that looks a bit like this, where we have some three-dimensional spacetime, three-dimensional, and we have some compact seven-dimensional manifold. Okay, so this is what we're going to do. And now I'm going to give you the recipe to come up with something like this, which is something that you have already heard about because Jason talked about it. And it's the heterotic issue system. And actually, this is going to appear also in Xenia's talk and in Magdalena's talk, I think. I hope. Yes. So by the end of the conference, you'll be very familiar with this thing. Yeah, so let me remind you what this is. And let me also set the notation because unfortunately, I have a bit of a different notation from Jason. So, but you'll see that it's exactly the thing I was talking about. So these are the ingredients that now I'm going to comment on. So what do we have? First thing that we have, well, our seven-dimensional compact manifold. So this has seven-dimensional manifold. And we want a G2 structure on our seven-dimensional manifold. But we want it to be integrable. So let me explain what this is now. Here, I think, Jason made my life very easy because he already introduced a G2 structure, so this is not something that you will be surprised about. So a G2 structure, which you can think of as a reduction of the structure bundle in D2. The way we're going to think about it is in terms of differential forms. This is what is going to be useful for us. So we have a G2 structure when we have some well-defined free form that satisfies some positivity conditions. What you might have seen is that people say that locally you can write it in a very particular way, and everyone uses a different notation for this. But so I'm not going to complete this, but hopefully this is not strange to you. As Jason already said, when you have this free form, you can construct a metric. So this automatically gives you a metric, a Riemannian metric. So implicitly there's a Riemannian metric there that I'm not showing you. You have an orientation, so you have also a hot star. And I can then produce this dual four form. We can go into another side. Good. So yeah, okay. So you have this structure, and now something that you can do, it's a natural thing to do maybe, is to take exterior derivatives of these forms. And yeah, something interesting happens because if you are used to the case of D2 holonomy or in SU3 holonomy, what happens is that typically these forms that you have are closed, so this would be equal to 0. But for a general D2 structure, this could be anything, a 4 form. But since we have this D2 structure, whatever we have here decomposes in D2 representations. So let me just write my notation for this. I'm writing here these taus, which are what we call torsion classes. Okay. Yeah, so this will be important for us because these torsion classes encode all the geometry that we have. And I promised I was going to explain what integrable means. And what I mean by integral is that I'm going to set tau2 to 0. Okay. So if I want to cook this thing up, I need to set this tau2 to 0. Otherwise, it just doesn't work. Nice. Yeah, so when in this integrable case, what the interesting thing that happens is that then you have a unique connection compatible with this structure that has totally antisymmetric torsion. And this is what it's called the torsion of the G2 structure. And let me just write it. The only thing I want to show is that really you just need to know the torsion classes. And then you can compute everything here. Okay. So this is the formula with my notation. Okay, so I've explained that part of the recipe. Actually, I've also secretly explained this last term because this is a 3-form Y, which in physics corresponds to some flux that is there. And what eventually happens when one looks at all these supergravity equations, etc., is that this flux is fixed to be this torsion tensor that I have down here. Okay, so that we have it as well. So let me.
Sorry.
Yes.
Even in the formula on the bottom, there, like, do you have the second term? There's a contraction of tau1 with side.
Oh, this. Yeah, this is just you think of it in indices. I'm just contracting indices here with maybe some factorial factor that I don't know by heart.
So tau1 is a.
Yeah.
It's a vector or.
It's a 1 form. I should have said this probably.
You use the metric to lower and contract.
Yes,
okay.
exactly. Yeah. Something I didn't say, maybe I should have said, is that the numbers here means like the degree of the form. So tau0 is a 0 form, tau3 is a 3 form. Yeah, thank you. Okay, and then, well, what do we have here? Here we just have a vector bundle and the tangent bundle. And I'm going to pick some connections in there, which have to be G2 instantons.
This vector bundle is defined over Y.
Yes, everything is over Y.
Then calligraphic M there is just the flat Minkowski space.
That's a very good question. I'll comment on this now, but no, it doesn't have to be. It can be also anti-de Sitter. And it's one of the interesting things.
Even with H living only on.
Yes. So even with, yeah. So even with H living only there, well, this H is it's a 3-form on Y. So in the full 10-dimensional solution, there would be a part with legs in the 3-dimensional space.
Then it's not only defined in Y.
Well, I'm calling this the Y part.
Okay.
No, but what I'm saying is that the part which is in M
I see.
splits completely from Y.
It's the couples.
The couple, yeah,
Right.
exactly. So I can just focus on the 7-dimensional part. And I'm forgetting all the 3-dimensional part, but you're right. Like with an antecedent, you would have a flux there.
Yeah, the 10-dimensional flux then will have a contribution, which is just volume form in 3 dimensions.
Precisely, precisely. Yeah. Yeah, thank you. Yeah, that's actually a very good question. And I want to comment on that very soon. Yeah. Okay, yeah. So I was saying that, but here I'm restricting myself to a 7-dimensional space. I can really just think of the 7-dimensional space. And yeah, so the G2 instanton condition, and let me just remind you what it means. It's just a condition on the curvature of these connections. And yeah, the easiest way to write it is like this. Okay. So we have this. So these are the ingredients. But of course, like to have a delicious dish, we need something to combine the ingredients. We need something to bring everything together. And what we have to bring everything together is the by now famous heterotic Bianchi identity. Which I would have loved to write here. Maybe I can fit it in here. Yeah, so the heterotic Bianchi identity relates H with the torsions of the connections, sorry, with the curvatures of the connection in a very non-trivial way. Yeah. And here, I'm a physicist, so I'm going to take my alpha prime to be positive. Okay. Yeah. So this is the very important bit. This is where the meat is. This, yeah, if you see, this is relating, for example, this torsion tensor. So this has information of the G2 structure with these instantons that we're building. So it's coupling everything here. So it's what makes the problem hard. Okay. Good. Yeah, the only comment I want to make out of this is that, okay, this is the recipe, this is what you need to do. But secretly, you're saying you're encoding all your physics information in here. And this is related to what Carlos was saying. So something that I really like, a good example of this is that the curvature of this three-dimensional space is proportional to minus tau 0 squared. Okay, which is this torsion class.
But this is, I guess, assuming a particular splitting for the spinors. How general is this?
So the way you start with this, you assume that you have some work product here.
You start with the 10-dimensional clean spinor equations, right?
Mm-hmm.
Okay.
Yeah, you start with the 10-dimensional clean spinor equations. Yeah, you write your spinors and you assume that they split. How general is this? So it's not the most general thing that you can have. I'm making some assumptions here for sure.
Let me rephrase.
Okay,
you will. This type of setup can accommodate for manifolds which are more general than just anti-de Sitter.
Here,
yes.
No, I'm assuming maximal symmetry here.
You assume it.
Yeah,
okay.
Yeah. Okay. But that's a very good question, and it's a very natural question actually. How general can you make this thing? And yeah, there are some papers by Graham, Papadopoulos, and Lorman where they try to study this in a very, very general setting, and it looks like you might have some extra things there.
Okay.
Although they don't give any explicit examples. But yeah, here I'm assuming maximal supersymmetry, maximal symmetry, sorry. Yeah. So that means that I can only have Minkowski or anti-de Sitter, thanks to this minus sign here. Yeah, and this is actually very interesting, and it went unnoticed in literature for a long time. So, of course, I'm not the first one to look at this thing, look at this recipe, and other people have done this. Yeah, this thing that we were commenting before, Fernandez, Ugarte, Villacampa, and Ivanov, right? Mario also has some solutions with tau equals 0, right? With Clark and with Kepler, right? Yeah. So yeah, and I think Jason was being a bit humble, not stressing this, that this anti-de Sitter solution until last year there was nothing in the literature. So, and for physics, anti-de Sitter is very exciting space. It's always nice to have anti-de Sitter for many reasons. Okay, good. I think I can now proceed to show you how do I fulfill the system, what things I throw in here so that we get a solution. So I'm going to erase this. So the first thing I want to do is to choose this G2 manifold. And in particular, so this is the preparation step. Yes, so let me stress one. First, let me look at this part. So the manifolds that we use, and it's just our choice, like you can do other things, but we look at homogeneous 3 Sasakian manifolds. In 7 dimensions, of course. Yeah, so a 3 Sasakian manifold in general, the way to think about it is what we were saying before, that Sasakian manifolds have the metric cone over a Sasakian manifold is scalar. For a 3 Sasakian is actually hypercalar. So it's a generalization where you have 3 Sasakian structures that play together. But we don't really need any of that. And in fact, in this talk, I'm just going to focus on the 7th sphere. So for the whole talk, I just want you to think of the 7th sphere. Okay. And another convenient way to think about 3 Sasakian manifolds, which is the one that now I'm going to show you explicitly why the 7th sphere works, is that you can think of them as some SU2 bundle over an orbifold. In our case, our 4-dimensional orbifold. And for the 7th sphere, this is just the Hopf vibration. Okay. Nice. And well, 3 Sasakian manifolds have a lot of nice properties. In particular, here in this SU2 part, you have 3 Killing vectors that satisfy some closed algebra. And I just want you to believe me that because of these nice properties, one can actually write some nice structure equations for these 3 Sasakian manifolds. So if I take some coframe locally, eta 1 to eta 7, okay, and then I can write this nice structure equation. I just want to write them to illustrate how you can really compute these things explicitly, and you can really find some solutions explicitly. Yeah, so yeah, Alejandro, I'm leaving a space here, so when you copy it, I'll be obvious why in a second. Same here. Here, yeah. And I have to tell you what these omegas are, and I'm going to do that immediately. So these omegas are just some 2 forms that locally we can write in a nice way.
First equation is true for that theta 1, 2, 3, right?
Yes, absolutely. Sorry, like I should have done that. Here I'm taking I from 1, 2, 3. Yeah, and 1, 2, 3. Thank you. Yeah, and 1, 2, 3 are the directions in this bundle. So I'm not showing explicitly all these eta equations, but in this case of the 7th sphere, you can actually compute every single thing. And these omegas are just some combinations of forms in this space manifold. So for example, I'll write one of them. And I don't know, I think you can believe me that the rest. So why am I telling you all this stuff? Just because, and now I can construct a D2 structure here. And the idea is really very similar to what Jason was doing. It's very interesting that we're working on these things and we're choosing like very similar manifolds to work on it. Luckily, not the same manifold. I think for me. Yes. So we can construct a G2 structure here. Okay. Good.
This one is the one that gives the round metric.
Yes. But I should say that because this is coming from the 3-second structure, it's not a G2 structure that this gives is not nearly parallel. Usually the round sphere has like the standard one is the nearly parallel G2 structure. This one is a bit different.
But the metric that
yes. Yeah, exactly. And now I'm going to do a little trick. That is, I'm just going to tell you one of the reasons why we chose these 3-second manifolds is because you have a natural family of deformations of these G2 structures. So this is something that is called squashing. So squashing. So yeah, rather than writing it, I'll just explain it. So essentially, you take the metric, you have some metric here on your coset, and what you can do is you can rescale this metric by a parameter, S, take to be positive. You rescale the metric along these fibers. So the picture that you should have in your head is that you take the 7-dimensional sphere, and you can do this procedure and squash it. So this is something that you can do. I'm really preparing the menu. I'm really squashing the dog here. And when you do this, you have this extra parameter, S, that now enters these expressions. And in particular, I get a family of D2 structures that depend on S. Okay. So there's an S dependence hidden here because of how I'm choosing orthonormal coframe, so it's hidden, but there's an S dependence. Okay. Good. Okay. Yeah, so the nice thing about this example is that then you can really compute the torsion classes that I was saying actually give you a lot of information, right? So you can compute everything. So you can compute tau 0, just going to write 1 and tau 0, which is something. So yeah, so things to notice here. First of all, tau 2 is equal to 0. So that's good. That's something that we needed to have this integrable D2 structure. And also tau 0 is never 0. So if this works, our solutions will have this anti-de Sitter spacetime that we would be interested in seeing. The dilaton is constant. The dilaton is constant, yes. Tau 1 is equally the derivative of the dilaton and it's constant, yes. So these are solutions with constant dilaton. Yeah, thank you, Mario. Okay, so now I've shown you how to do this. And again, secretly, because I have all the torsion classes, I've shown you how to get this page. So we just have to talk about the bundles and these instantons, right? So I'll do that now. And again, I'm going to use, so here I'm just going to present like a particular example But in our preprint on archive, you can see that we played with different instantons. We tried to construct different instantons and we played with them to see if they were giving us solutions or not. I'm just going to present a particular case. So for this one, for the vector bundle, what I'm going to use, and then we're going to use something called the canonical connection. So in this 7-sphere case, you can think of the 7-sphere as a coset space, as a 3-second manifold, as the spin 5, and SU2. So this gives a natural SU2 bundle over your 7-sphere. And yeah, believe me, I'm not going to go into details, but there's a very classical way to construct an connection here that in this case is a G2 instanton. You can read about this in Kobayashi no Mitsu, actually. So we get a G2 instanton, in this case on an SU2 bundle. And yeah, this is a principal bundle, and here we need a vector bundle. So we actually have to take a representation of the bundle, a vector bundle associated to this by taking an SU2 representation. So we, for example, for this example, I'm going to take the adjoint representation. Good. And then for the, for this tangent bundle, which is the one that, for the one that Jason we're having a bit of trouble here, we actually managed to find a 1-parameter family of G2 instantons. So, and actually, I have here written the torsion in terms of the torsion classes. So you can really write this. And this is coming from the fact that on a G2 structure manifold, you always have a 2-parameter family of connections that are metric and compatible with this G2 structure. And this family, in our case, collapses to a 1-parameter family. And we can show that in this setting, it gives us all of these connections are G2 instantons.
Does this family include a connection with skew symmetric torsion given by A?
So I think it does. In a particular case, it does. Yes, I think. Or no.
Which the same sign as the metric connection with torsion that preserves the G2 structure, or with the opposite?
Yeah.
The same.
I think it's the same. Yeah.
Is it the same norm as well at the top?
Sorry, what do you mean by norm?
Well, number of bismuth is +1/2.
Yeah. I know that's what you're asking. Yeah. I don't.
The whole connection is not an instant.
Yeah, exactly. I don't think you have that. Yeah. Yeah, I don't know. I would have to check it if we do. Huh? You think it's the same sign? Yeah. Okay, we can check it later. Actually, thanks. Yeah. But yeah, we have a 1-parameter family here.
These are complicated expression, right?
Yes, I mean, there is an expression. I can write it, but I'm not going to write it. But it's on the paper if you want to have a look at it. Yeah. Okay. So now the only thing left to do is to actually, in these last 3-4 minutes I have, I'm just going to tell you that we take all these ingredients, we put them in the oven, and we check if we can explicitly compute all the curvatures, everything here, and we check if we can satisfy this condition here. Okay. So we do so, and actually we can. So let me explain to you this particular solution that we find in this case. And then I'll comment a bit more on this. Okay. Yeah. So what is the result? So here we have this one parameter family of connections, this other connection, and we have also this freedom to squash sphere. So if we write the solution in terms of this squashing parameter, actually I can tell you that this connection, like this is the parameter of the connection, has a very simple expression. And yeah, let me write alpha prime in terms of S, just because it's easier. And then I'll comment a bit on alpha prime exactly on what is going on. If I draw these quantities here in terms of the squashing parameter, what we find is that like this A has something like this. And the alpha prime.
Is this a region or a vertical?
Yeah, sorry. This is a. Yeah, there's a simple here. I'm just telling you as you move S, what's the value of A, which is a number. And alpha prime does something like this. Tends to 0 here. Yeah, okay. So the only thing I'm saying here is that this alpha prime. If you tell me a value of alpha prime, and it can be as small as you want, it's positive, I can go here and tell you exactly an S and a value of the connection such that I find a solution. Okay. Nice. So, okay, so now, so this is the result in this particular case. To finish up, just let me say other things that we do in the paper.
Are the solutions exact, or you are taking into account this perturbative expansion?
My solutions are exact. Exact and alpha prime, like, yeah, these are G2 instances. Like we do.
Yeah, but the full system is satisfied exactly equal to 0, or there is equal to O alpha prime something?
No, I don't put any. Yeah, we don't put any O alpha prime square or anything. We just really take these equations and solve the heterotic Bianchi identity as it's written there.
The full system.
Mm-hmm. Yeah.
It might be worth saying that the vertical asymptotes are where the Einstein metrics are.
Yeah.
Honestly.
Yeah, thank you. That's a good observation. Yeah.
S is 1 is the round metric, and S is 1
Yeah.
for root 5 is the other one.
Yeah. So in this particular case, this is what we find. Yeah. I was keeping it, but it's remarkable. Yeah. So yeah, with our method, we cannot really find a solution here for this.
For the Einstein
case, which is the nearly parallel G2 structure in our case.
Yeah, but this is probably a manifestation of the fact that if you solve the system and these are generalized Ricci flat, or you are solving the negative equation for motion, if the Ricci drops, then probably you cannot have a solution. I mean,
Makes sense.
Yeah. Maybe. Yes, and point.
so how is the metric? Because you didn't write it.
I didn't write the metric.
It's very complicated.
No. The thing is, I'm hiding it all the time.
Just the squash one, isn't it?
Yeah.
Just
Just a squash metric. Yeah.
So with this frame, it will be just have an S maybe in front of the.
In front of the S2. Yes.
First eaters.
Okay.
First 3 eaters. Yeah.
Yes. Exactly. Yeah.
And there is also one over S in the other two.
No.
Okay.
Yeah. Good. Okay. Yeah. I'm running out of time, so I'll just say that this is a particular solution, but we have a bunch of different solutions, and something that is particularly interesting that we did manage to find. So let me just advertise it here. We did managed to find a one parameter family of solutions, parameter family with alpha prime fixed. So why is this nice? Because this connects a bit with the work of Xenia with Magdalena and Eric as well, and also with Mario's work with heterotic with Clark and Tipler, yeah, where they study the moduli problem, the moduli space of the heterotic D2 system. So this is a finite dimensional version of this. This is like if you want one direction in moduli space, you can take some alpha prime fixed, and you can then there's some region where you can squash your sphere and move your connections in such a way that you still find a solution. Yeah, so this probably makes also Gil happy for saying that he wanted to fix alpha primes. This is something that we managed to do in our case. Yeah, so maybe, yeah, I think I'll stop here. Thank you very much.
Comments or questions for Mateo? Yeah, please.
Yeah.
So since you now have a one dimension, so in this case, you know that you have the dimension of moduli space is at least one dimensional.
Yes.
Is there any hope of computing if comparative or figuring out the dimension?
Yeah, so I guess here's something if I didn't have to write my thesis, probably I would be trying to do these things, I guess. Yeah, so yeah. But yeah, that's exactly why we started to do this. We really wanted to kind of connect with your work with all these, where you compute these cohomology classes that actually tell you how to deform the space. And here what we find is one particular direction, and I've done a very particular squashing and deforming my connections in a particular way. But I don't have any reasons to believe that. I think that actually there's much more than this. Probably you can deform your method in a different way and still get a solution.
This is a very explicit geometry, so maybe you have a chance of computing it explicitly.
Yeah, I think that we haven't really looked at it like in a lot of detail, but it's something that we definitely want to do next. And a lot of people have worked on, I think G2 instantons on the 7th sphere with their own metric. There was a paper by Waldron a couple of years ago where they really looked at all the instantons and they were really trying to find instantons on that tangent space. So that's the kind of stuff that we could try to use to really see the whole moduli space. But for now, I have nothing more to say, unfortunately.
Is there an expected dimension for this moduli space?
I don't know. And we know that it's finite dimensional. It should be finite dimensional, but I personally don't have any beliefs or any indications.
Can you just summarize what the level of symmetry is in this family?
Sure. Yeah, what do you mean by the level of symmetry?
Well, when you find explicit solutions like this, usually it's because there's a lot of symmetry.
Yeah.
Perhaps it's even co-homogeneating one. I'm just wondering, what's the symmetry?
Yeah, that's a good question.
Are these homogeneous, in fact?
Spin
Yes.
5, I think.
They are homogeneous.
Spin
right?
5. I think.
Yeah. So, so I think it's true that I think the reason why we find solutions is because these are just because of these. I erased it. Yeah, but just because we're looking at this S7 as an SU2 bundle. So this splitting in the bundle and the base plays a very important role. For example, when computing this identity, because all these curvatures and these DH really split in of the bundle and the base part a little bit.
Okay, but does that mean that the spin 5 is acting on all the structure? It's really
I think
the whole solution is spin 5 invariant.
So I think
It's just
I think that is true for the. I think this is true. It's true that the spin 5 acts on the whole solution before you start squashing. Once you start squashing, you lose the 3-second nature. So I think this spin 5 symmetry breaks down.
No, it's still there, but it's only now left invariant rather than bi invariant. We'll still have spin 5.
I see.
Could you say? I think
It'll just be left invariant though. I mean, it's not the bi invariant. You still have spin 5 acting It's a homogeneous space.
Well,
Yeah,
yeah,
it's still spin 5 symmetry,
But
but it's
you're
just
speaking of the symmetry group of the entire solution, right? It acts on the bundle, it acts on everything.
everything, but spin 5 invariant, I think. I mean, I haven't looked at it in detail, but that's what it looks like to me.
But shouldn't it then act on the sphere and give you a bunch of isometries of the sphere? Like, yeah, but the sphere is squashed, like. Well,
Yeah, but it's a spin 5 invariant metric, but not bi-invariant.
just
left invariant.
Left in. Is the left action of spin 5 on a sphere transitive? Like I'm having trouble imagining a sphere being squashed and having a group acting transitively on its isometries.
But that's what happened. I mean, that's this expression. You can write this one parameter family of things. It's a totally geodesic, fibers.
It's not
yeah. I'm not sure.
Still is just by the look.
Yeah, it's the left action. It's just like the whole
Yeah.
vibration base 3, right? You can write the Berger metrics. There's still SU2 invariant, but not
Right.
bi-invariant, just left invariant.
Right,
It's exactly the same. You can do even more crazy squashings than this.
So Mario,
Jason.
go ahead.
Yeah.
The geometry you have really suggests that you can study this non-abelian duality studied by Xenia de la Osa and Fernando Rodriguez Villegas in this solution. So did you explore that?
So we haven't explored it. It's on this to-do list that I have here, things that we could do next. But yeah, like it's definitely very tempting trying to do some non-abelian duality and see what comes next. Yeah, and yeah, we've been trying to think about duality with Xenia and with Enrico Marqueto, another student of Xenia. We're really thinking about duality, and I think this is a good example to try for sure.
But then if you do T-duality, you cannot do it in 7 dimensions, right? It's because T-duality sees the full flux, so you have to do it in 10 dimensions, right?
Yes, I probably, yeah, I think,
What's the coupled, right?
Yeah, but even if the flux decouples, if you want to build now the T-dual of the solution, it should be the T-dual of the 10-dimensional Lorentzian solution because it sees the whole flux, and the T-dual may have a contribution from the Lorentzian part in the Riemannian side of the dual solution.
yeah, I think that is
When you're talking
correct.
about abelian duality or
Even in abelian duality.
But Mario had the whole geometry set up for heterotic things that included the G2 case that then it's separate. But
No, but this G2 case is different from the one that Mario considered. Because this is associated to a compactification to ADS3,
Yes,
which carries non-trivial flux.
Yeah.
It carries real killing spin-off, right?
yes. Yeah, that is correct. It's a bit different.
So I would be very curious to see that type of T-duality in action.
Yeah, go ahead.
Okay, sorry, I had another question.
Yeah,
So
absolutely.
you have this nice paper with Fisset
Yeah,
about the I don't know how to put it in your words, but vertex
Math.
algebra really,
Yeah.
and these twisted connected sounds.
Mhm.
Is there a way of relating what you're doing here, these solutions?
Yeah, so in this, yeah, thanks for the advertising. Yeah, in this other paper, what we do is we take out of a different perspective and we look at also like this kind of heterotic G2 system, but from a worldsheet point of view. So we look at the conformal theories in the worldsheet when you regard this as a sigma model. So you have some vertex algebras arising there. And what has been studied quite a bit is the case when you have some G2 holonomy. You have like these sigma models and the target has G2 holonomy. And in the G2 holonomy case, this 3-dimensional part has to be Minkowski, it cannot be ADS3. So in this case, the worldsheet algebras will be a bit different. And he said that a paper with Matthias Gabriel where they do like some ADS3 cross, I think it's S3 and T4, something like that, and they try to play this game and they do see that the algebra changes. So there's some effect on the vertex algebra. The vertex algebra knows about these fluxes that are there. So yeah, I think that's something that we could try to do here as well and see if we come up with the same algebra or an even more general one. I haven't tried it.
Well, I think further comments can be brought to the coffee.
Yeah.
So.